In this video, we will learn about the Bayes rule. Bayes rule, first formulated by Thomas Bayes, a British statistician, computes the probability, conditional probability of A happening, provided that B has already happened, as the probability of B happening, provided that A has happened, times the probability of A divided by the probability of B. This rule is a very useful and important rule central to the Bayesian decision theory. Let's look more closely at this rule. Let's have some examples to understand it better. Let's say PA is the probability of raining in a day, and PB is the probability that the day is cloudy. PA, provided that B has happened, is the probability of raining in a cloudy day. And PBA is the probability that a day which has some rain in it being cloudy. We know from experience that this probability may be close to 1 because most of the days that have some rain in them are cloudy days. But there are some days that are rainy but not cloudy. So let's say the probability of this day, this incident, is 0.9. So in 90% of the days that have some rain, we see clouds. PA, let's say PA is 0.3. Probability of raining in a day, irrespective of it being cloudy, is 0.3. And probability of the day being cloudy is 0.5. These are made up numbers. I just made them up to illustrate a point about the Bayes rule. They are not real in any ways. Before going into the formula and calculating the value of the probability of A, provided that B has happened, let's think about these probabilities. PA, provided that B has happened, and PA, irrespective of B happening. So probability of raining in a cloudy day with just probability of raining. Should this number be bigger, equal, or smaller than PA? In other words, is the probability of raining in a cloudy day bigger, equal, or smaller than the probability of raining in a day we don't know anything about? Pause the video and think about it a little bit. As I'm sure you agree, the probability of raining in a cloudy day is greater than the probability of raining in a day we don't know anything about. And that's the effect of this piece of valuable information. If we know the day is cloudy, we know that it has more probability for raining. But let's get into the numbers and calculate the value of it according to Bayes' rule. According to the Bayes rule, PAB equals PBA, which we defined as 0.9 here, times PA, which we define as 0.3, divided by PB, which is 0.5. And if we calculate this, we get the number 54%. And we now have a quantitative number for our intuitive understanding. Here we understood in this formula, we understood that PAB should be bigger than PA, but we didn't have a number for it. How much bigger? And here we have a number for this. And you see, as PB goes up, as the number of cloudy days go down in a year, because if the go up, sorry, let's say, let's think about it this way. Let's say if the number of cloudy days go down, if we have less cloudy days, and this goes down, this goes up, this number goes up. So if, for example, it's 0.4, this number is bigger than 54. And that's a very important point of the Bayes rule. And that gives us the value of this information. If the probability of B happening is low and we know that B has happened, that information is more valuable. If the probability of B is close to 1, let's say probability of a day being cloudy is close to 1, it doesn't change. It doesn't change. It doesn't increase this, because knowing that some day is cloudy doesn't have any information in it, because almost every day is cloudy. So this is a very important aspect of the Bayes rule. Let's go deeper into this and try to prove the Bayes rule. Let me draw some shapes first. Let's say this is a Venn diagram of our aforementioned problem. Let's say the bigger rectangle is the total number of days in a year, and A, this ellipse is A, and this is B. The probability of A would be the area of shape A divided by area of shape E. And it's because actually the value of the probability would be the number of the elements in set A divided by the number of elements in set E. But in Venn diagram, we map the numbers to the areas of the shapes. So a shape with a bigger area would have the proportionally bigger number of elements. So we just use areas because it's easier for us. And for some uncountable sets, it helps very much. And PB would be SB divided by SE. Okay, so far so good. But let's talk about PA provided that B has happened. We know B has happened, so this changes the total possibilities. Here we know that everything could happen, so everything could lie in E. In this formula, we knew that everything could happen. The total number of possibilities lied in E, but now the total number of possibilities lie in B. So here in the denominator, we should have SB, because we cannot go anywhere else than B. And here we know that B has happened, A has happened. So we know that the only place that has this property is here, the intersection of A and B. So it would be the intersection of A and B divided by the area of the intersection of A and B divided by the area of B. And if I do some algebra here and divide the numerator and the denominator by SE, the same number, I would get the probabilities. So I just divided denominator and denominator by the same number. Now I have P A B equals P of intersection of A and B divided by PB. Let's talk about PBA. In this formula, we are just exchanging the role of A and B. We didn't change anything. Let's just write it down as this. We could have the same analogy for this too. So it would be PB, provided that A has happened, equals the probability of B intersection A, which we know equals the A intersection B, because intersection doesn't change about the order the sets come, divided by PA. So let's call this the formula 1, and let's call this the formula 2. If I calculate PA intersection B, PAB for the first formula times PB, and again we will have PAB for the second formula, PBA times PA. Now we have two formulas with one side equal, formula 1 and formula 2. We can equate the right hand side of these formulas, so it would be PAB times PB equals PBA times PA. And if I write it down with PAB in one side, it takes the form PBA times PA divided by PB, and which is basically the base formula which we learned about in the beginning of this video. We here saw that we can use the Bayes rule to calculate the probability of having extra information. And then we learned how the Bayes rule works out if we write it down in terms of the Venn diagram. We kind of proved the Bayes rule. I hope you gained some intuitive look and understanding into the Bayes rule.